So yeah, machine learning in general, there are tons of different methods to basically making predictions on data. And this first part, just because I think it's generally the most intuitive, we're going to be covering tabular data in particular. So this is basically anything that doesn't really have a natural sort of sequence to it. So something like a light curve would not be a very good candidate for this. I wouldn't call that tabular data. You could try tabular data methods on it, but it's probably not going to work out too well. But either way, this is a good place to start. So for that, going from that, there are generally two types of machine learning. It sort of falls into supervised and unsupervised learning. Things along the lines of unsupervised learning would be stuff like dimensionality reduction, principal component analysis, anything along those lines. So this is where you don't have any labels for your data, and you don't really care about like a specific outcome of your neural net. You're just trying to get whatever the neural net thinks is, or well, neural net's a pretty bad idea, but a bad example of it. But whatever your machine learning model, thinks is best, that's essentially your outcome. Supervised learning, on the other hand, is when you do have things like labels for your data. So in our case, things like, oh, we know this is a type 1a supernova. Oh, this is a type 2 supernova. This would fall under a more supervised learning problem if you're actually applying that to your model. And the very core foundational idea of neural nets, at least, is an object called the perceptron. So perceptrons, they were initially, come up with in 1958 by Frank Rosenblatt. More along the lines of like, oh, trying to figure out just how brains work and how we sort of process things along those lines. I don't know. I'm not a neuroscientist, but there were things before this as well. There was one, I think, in like the late 1930s. It wasn't technically the perceptron algorithm, but it was very close. So I'd put that in there, but I wouldn't put it in as a slide. So yeah. But what a perceptron algorithm actually is it's just a linear sum. It's a weighted sum with, just straight up linear weights, and you're getting however many inputs you have, a weight for each input, and then one output. That is the perceptron. But that's just a weighted sum. So this doesn't really have any like, when you think of neurons, you think of an activation sort of thing. So what you put on it is an activation function. Oh yeah, and here it is in multiple, whichever format you like, whether it's Einstein summation notation or linear algebra. Yep. All right. So what we do is we put it through an activation function. So whatever comes out of the sort of the linear sum, we put it through one of these kinds of functions. Sigmoid is a pretty classic one for if you're trying to get probabilities, because it scales every sort of real number, because your perceptron could theoretically output any real number from negative infinity to infinity. So if you want to compress that down to get an actual probabilistic output, you put it through this equation here. It's known as sigmoid activation, and then it perfectly maps what you have to an actual probable output. From there, then you have things like the ReLU, which is the rectified error linear unit, something along those lines. But this one is your classic sort of actual activation, where it's like it's either turned on or it's turned off. And while it may not seem like just combinations of a linear weighted sum and an activation function can get you very far, if you end up actually layering them in what's known as a multi-layer perceptron, you can end up representing some pretty interesting functions. So this is sort of the foundational idea of what neural nets are, for inference, at least. So for now, just pretend like you have the perfect weights set up for your model. We'll get to how to actually calculate them. But, and yeah, again, in terms of linear algebra, once again, these are just linear sums. And it's just more layers now. But these, again, still don't represent too interesting of functions. So the sort of deep neural nets start arising. These are when you're really like focusing on layers rather than width. And you can, as you can imagine, get more and more interesting functions. But that brings us to, okay, well, how do we actually get the weights for these things? Because it's not very helpful if you can't actually do anything with it. If you just have this theoretical idea that you can represent things, but you can't actually do it. So to do that, you need to actually quantify just what it is that you're looking for. And this is essentially the motivation for the loss function. So there are plenty of different kinds. In this example, we'll be, for actually calculating weights for that example, we'll be using mean squared error. But a more common one is cross entropy loss. There's binary cross entropy loss. Felipe likes focal loss. There's like dice loss, which is really bad, but kind of interesting to put in. You can put it, you can come up with all kinds of things. In fact, in the example in this notebook, I have using the great circle loss, which is kind of interesting. We'll take a look at how that works. Either way, so using this quantification of our error, we can actually figure out how we need to get the weights to change based on just straight up guess and check. Well, initially it's guess and check. You're basically just feeding it random values for whatever the weights are initially, and huge samples. This is why it's very important for a big sample size of data. But yeah, for each, you're just sort of giving it whatever you want. And then you actually want to, okay, well, let's see how, how this actually affected our loss function, or our end loss, I guess. So yeah, you want, like, for probabilistic outputs, because this is generally a much easier one, it's literally just 1 if correct, 0 otherwise. Pretty simple. And yeah, so the actual math for for people who want derivation is right here. You're basically, for mean squared error, you are just taking the mean squared, getting the derivative of the mean squared with respect to whatever weight you're currently trying to find, the optimal weight for, and put it essentially multiply that by what we call the learning rate, and then you can end up getting your new weight for your next iteration of training, essentially. But all of this, not too helpful. So let's just immediately hop into an example. And this example, you don't need to have downloaded any data. We'll get to that. But anyways, for this one, you should be able to, if you install the requirements. There's a requirements.txt file in the day 1 folder. To install requirements, you should be able to just run this. So either way, what this is doing, a classic situation is, oh, well, we have this one kind of coordinates, equatorial, which is not based on the equator, but it's more equator of the sun. Because you want the sky to stay in the same location. But there's another kind of coordinates, which is, hey, if we want the galactic center to be, coordinates, and that's very helpful for finding extragalactic things. So just to show you how these activation functions combined with just linear sums can represent some pretty funky transformations. Let's train one to transform these. Yeah, okay. Actually, I'm going to stop screen share a different Hold on. Okay. I want to be able to actually run this just because I think it's interesting. Um, uh, this. Come on. Why didn't stay up? Uh, this is awful. Why is yeah. Uh, anyway. All right. Okay. All right. Yeah. Okay. Perfect. Uh, okay. All right. There you go. So, um, quick, I left these so that they should just run, and although the imports takes a little bit to run. But basically the gist of what's happening here is we're just making a bunch of random points on the sphere and just calculating what they are in both equatorial and galactic coordinates. And now obviously we want to actually see how well we're doing. So um, just before we do anything else, also put in a function for um, basically just what percent of our output samples are within 1%, 1 degree of the correct location. Okay. Anyways, there we go. Okay. And in terms of the actual model architecture for this, just to show you that you don't really need a whole lot of layers to get something pretty interesting. Um, this one, it's just 3 blocks, 6 layers total. Well, unless you're combining activations into the linear layers, some people do. But yeah, 6 layers total. It's pretty simple, but if you actually, there we go. If you train this, you'll get pretty good scores. Now, a bit of a caveat to this, training logistics, in terms of how we actually do this in practice and not theory. What we essentially do is we first split the data into 2 sets, a training data set and a validation data set, for reasons that will soon become obvious. Training data set is then segmented further into what we call batches, which are equal sized, just portions of the samples. And this is done because your graphics card, when you're dealing with an enormous data set, probably can't handle all of them at once, unless you have a very interesting graphics card. But yeah, so you size them into batches, and these also have an additional caveat that I'll get to later. But yeah, basically, so for each sort of training cycle, I guess you could call it, you're going to have a set number of epochs, and when epoch is that full sort of okay, inferencing, getting predictions from our model, and then going back, calculating the derivatives, getting the new updated weights. So that's one sort of cycle, you could say, from that. And in each epoch, we do one of those cycles for each batch. So the batches are done in succession, but inside, when you're actually doing it for a single batch, things are happening, well, hopefully parallel, depending on your graphics card setup, but that's going into weird hardware-like stuff. So you can think of it as, okay, they're all getting calculated at the same time. But the important thing is to know that, the batches are being done in sequence. So yeah, inside each batch here, I have basically a diagram of, we'll sort of run down some pseudocode. Yeah, I don't know if I can explain it better than that. Oh yeah, the weights are in practice. Also, the weights aren't, since we're not doing derivatives by hand, that's handled by what we call the optimizer, and the learning rate. You, as you'll see soon, you usually want that's going to vary throughout your whole training cycle. or whole training run, I should say. So you also have that handled by what's called the scheduler. All right. Now, the reason we're splitting the data set into two, or at least two, is a thing called overtraining. So this is kind of the bane of machine learning. This is what you will usually be fighting, and that is basically when your model, whatever it is, starts learning relationships that don't really exist in the actual world. So these are things that only really kind of exist in that specific data set and just do not generalize at all. So this is a good example here. Sort of, you can see that, okay, the obvious actual relationship is this, but then, okay, if we have a pretty small sample size, it could start doing some weird sort of zigzaggy thing where it's like, yeah, it's hitting every sample perfectly, but like, okay, that's not a real representation of the data. I mean, that's just going insane at that point. I mean, that's not at all what it is. So this is exactly what overtraining is. And a method to prevent this is essentially early stopping and controlling the learning rate. So the validation set, the purpose of that is so you can continuously track the performance of your model on some data that it hasn't seen before, it has no sort of reference for, and that does not show up anywhere in the training set. I'm really emphasizing this because it is extremely important that data does not get leaked between these things. So yeah, here we go. I set up a training script here just for people to play around with. Right now, it is set for a ridiculously high 200 epochs. It continues to improve well into the 100 epoch on this specific problem. But I'm not going to lie, I think you should probably cut it at about 30 or 40, just because it takes a long time. And a lot of people, yeah. If you want to really learn things, a lot of runs is important while changing things. So yeah, you should be able to run this. And here, if we run this, oh, God dang it. Hold on. That is, what? Oh my God, yeah, I didn't run the cells before. That's my fault. I'm just being dumb. Yeah. Okay. Whatever. I know that's fine. This thing in the way. Here we go. Okay. Okay. All right. Yeah. I also set this up so you can sort of see it going through the training data as it's training. So right now this one's doing 70-ish batches per second, which is fairly nice. Yours may be going faster or slower. But as you can see, it is slowly like working its way up towards being actually accurate. And just a reminder, the training accuracy and validation accuracy, that is the percent of samples that it's guessing correctly within 1 degree. So it's getting pretty decent fairly fast, and that's not even close to a linear relationship. So I'm pretty happy with that. Anyways, basically, this isn't super informative though. I'm just gonna cap this off here. There we go. As you can see, hope now in a perfect world, this would be much smoother. If I keep letting it run, it will be smooth. It'll be smooth at the very end. It's pretty hectic early on because the learning rate's fairly high. But the scheduler, as we'll see, takes care of that pretty much. But the validation and training loss being very close, that is a good sign. If your validation and training loss are different by like 5% or something around along those lines, it's not too good. Keep in mind orders of magnitude though. That can screw you up. Sometimes if the loss is really, really tiny and they're like, one is twice that the size of the other, but they're super, super, super small, that's okay. It doesn't matter as much, basically. But yeah, this isn't super informative because we're significantly more worried about where it's going right or wrong. And, so a thing that we can do pretty easily is we can actually plot where it's going right or wrong by just plotting the error as a function of our inputs. I set up a function here for that. Here we go. Should be pretty decent, actually. That's a little bit better than I was hoping. This line keeps showing up. It's really hard to get super close to zero for certain things. This line gets thinner and thinner the better you do on your model, though. So pretty much have fun. Go try changing the model. Currently it's set up just for these three blocks, but I'm telling you right now, you can improve this a lot. I gave you a pretty bad one. So there are a couple suggestions in there. Yeah, pretty much let me let any of us know if you have any questions or need help.
How long doing them stuff?
For this one, this one probably about like I don't remember how long the rest of this one. Okay, yeah. Probably let's say like 20 or 5 minutes, somewhere in there. Working in the first one for some reason. But it's in the day 1 notebook. The first one was day 0.5. This one there shouldn't, yeah, I believe I got rid of all of the bad imports, so fingers crossed. Either way, so a big issue with training neural nets is just training them in general. One of the amount of time that it can take to train these things is enormous, and it makes iterations really, really annoying. If you want quick results, neural nets don't really get you them when you're trying to change architectures, at least. Really quick predictions, but actually building them and getting them to where they can make good predictions takes forever. So a very commonly, actually, I just realized there's no, where's the thing go? Oh my God, okay, yeah. So a commonly used tactic is pre-training. And what pre-training is it's essentially taking models that have been trained on either your own data set, but more often someone else's completely different data set for a completely different problem as well. And so you may not think that that is very helpful, but it turns out that models that are really, and the one on the bottom is in actual galactic coordinates, like what your model was just trained to translate between. So this is a set of, I don't remember the exact number, but a good amount of cataclysmic variables plotted, from the right transient survey plotted on, as a function of galactic coordinates. You can see there aren't any in the dead center of the, galactic ring, but, because we're not really observing there, but tons of them around them. And, it definitely gets closer, the density of them increases as you get closer to the, galactic radius, or galactic disk, I should say. And if you're wondering why there's a whole hell of a lot more on one side than the other, it's because we're not in the center of the galaxy. So, so, obviously this isn't a 100% like, okay, if we see something and it's like pretty close to the galactic plane, then, it's not a whole 100% chance of being a cataclysmic variable, but the odds definitely go up a lot higher. Because of this, we're going to use our pre-trained neural nets that already has a sort of idea of, okay, spherical coordinates in general. And we're going to train it to, add another layer to take the outputs and turn them into a probability of whether it's a cataclysmic variable or not. So to do this, it's not too difficult. As you can see, we're actually calling the exact same MLP that we made earlier inside of this different sort of neural net module. And then we're going to actually load in the weights that were saved in the last script. I didn't point this out, but there is a torch.save function getting called or method getting called in the training script that you were just running and playing around with. That was saving your best model. So whatever you had for your last run, use that one. Even if it's not the best, just use it. Unless it was truly terrible, then you can retrain. But if it's we're halfway decent, just use it. We're going to be fine tuning anyways. So yeah, it should make sure that you have the path right. If you change the path, if you didn't change the path, you should be good. But yeah, it's still good to keep that in mind. Oh yeah, and also, this is a different data set, fundamentally. I've taken care of most of the issues of, most of the things. I did leave a couple issues in there for you to figure out. And those are kind of, oh, yeah, dang it. Oh, well, that's okay. I thought I accidentally deleted a comment, but either way, one of them is that you will need to change the classings that we're actually looking for. The actual notebook I uploaded, I believe I left it as 3 classes instead of 2. We just want to decide, we just want a model to tell us whether it's cataclysmic or anything else. You can kind of see how it's structured here. Yeah, there's what this is mislabeled. It could be basically anything. This is just gonna be what shows up on our plots. But either way, the whole point of this is just to show you that you can sort of nest these neural net modules, and you really are building them like blocks. And also, you can indeed just retrain models. Totally different problems with the same weights as before, and it should improve things. It usually does, especially when loss functions are not necessarily perfect always. And for the last problem, we pretty much did have a perfect loss function, which was because we were able to get the actual distance from the point that it was supposed to be versus the point that it actually was. So we're going to sort of take advantage of that by putting in this one.
You're muted.
I'm muted.
Yeah. I think he's going through Michael.
Yeah, it's going through Michael's thing. It should. What? God dang it.
Wait, did Michael connect his headphones accidentally? Somebody mute Michael.
Michael, wait. God dang it. Okay.
His audio's on and it's saying it's working.
What?
That's what he's in right now. That's just refreshing.
Eh.
I can go in mine.
Does the owl require, so the owl require Bluetooth?
Okay.
I don't know. I mean.
It's saying
Do you have a Bluetooth off your laptop?
I turned it off. I thought. But I didn't need to be.
Okay.
Can you hear us now?
God dang it. Okay.
I didn't hear us.
All right. Okay, let's go over again. Basically now we're going to switch into sort of putting these sort of neural net modules together like blocks. The first one is just using our pre-trained equatorial to galactic multi-type perceptron model to create what's the likelihood that this is a cataclysmic variable based on just its coordinates, the coordinates going into it. Now there's one caveat to this that I didn't get to say that yet. This is being passed a large amount of data. Way more than we actually need for just getting the input coordinates. So to handle that, you can see that this forward pass has just one straight up metadata thing. We're only going to pass it the two metadata points that are actually important, which is the galactic longitude and latitude, L and B. In this specific case, the indexing for that is already put in. So, and you'll see all the indexing is taken care of, but that's essentially what's going on. This isn't getting past the entire metadata set, but only two of them. Yeah, anyways, go ahead, have fun with that. I will say, just because a little bit behind here, next part. Oh, let me scroll through this. Auto scroll turned off, excellent. All right, very last part. Is combining these. You can see that you can do this with a bunch of other metadata parts as well. So that one is just taking taking the coordinates, finding the likelihood of something being a cataclysmic variable. But the other metadata stats are important as well. So we have a whole host of them. I would go over all of the specific ones, but that would take too much time, and I don't think it's super important. I think it's more important to just show that like we've already split up the actually important metadata features for each one of these sort of things. So this is light curve features. So these are things pseudo related to light curve. You know, how long does it take for an object to reach peak brightness? How long has it been since it reached its last peak brightness? Along those lines, spatial tower is just for spatial distances. So how many objects are nearby it, essentially. And nearest tower is, okay, what information can we get out of the nearest object in the Pan-STARRS catalog to whatever object we actually care about. So each one of these, there's currently an unmade tower. You can make tower. You don't have to pre-train them. I put in this, pre-training stuff here, but you can comment them out and, just not deal with that at all if you don't want to. The important thing, oh yeah, same with the actual image branch. You don't really need to use it if you don't want to. Most of the actual information is going to be coming from the metadata. The images can definitely help a lot, but you can also still do very well with just the metadata. Now and down here you can see the indexing is already filled out. There's a ton of things commented out here. You can explore here. There's a mixture of experts model in here. I can get to that if people are interested in it. It's not super helpful here, but it is fairly interesting, I think. And it can be applied to pretty much any kind of neural net. And it's what's used in pretty much every really big large language model. Pretty much all of them use it. DeepSeek made some recent-ish contributions. They called it a DeepSeek mixture of experts. Currently the image section isn't plugged in, but if you uncomment that and fiddle with this, you can figure it out. Basically that's it. The actual features getting combined here, I do want to go over that real quick. All we're doing here for these ones is just concatenating them. So each one of these individual sort of neural net towers will output a fixed vector, essentially, per sample. There's, however many samples you have in your batch. And so a very common kind of feature fusion, I suppose you could say, is just going to be concatenating them. So stacking them on top of each other, making a single longer vector, by doing that, and then passing it through a completely different multi-layer perceptron, you can basically get at a pretty decent fusion model. That's a very common way to do this. I already filled that in at the very bottom just because for at least one example here, which is a tower that's getting past every single piece of the metadata. if you were to put, oh wait, sorry, no, this one, this one's meaningless, but if you were to, this one, each one of these is the features coming out of a single, one of those blocks. You can concatenate them like this, make sure that you specify the dimensions, otherwise things will break, and it will think that you have twice the batch size that you actually have. That's a very important thing to keep in mind. Basically from here, you can play around with this. Make sure you get the routing right. I left a couple mistakes in here for people to find. Hopefully they shouldn't give they shouldn't give super misleading errors, but if they do, please let me know. We'll help you out. Yeah, basically have fun with this. Try making as big as model as you can. And for each one of the actual towers, try finding the actual classes that they can best differentiate by changing the grouping up here. You should be able to find the one that works best, either by just experimenting or looking things up. You can just ask some chatbot if you want, like, okay, which groupings make most sense for individual modalities, or if you want some help, I can help you as well. So yeah, just really have fun. There are a lot of things you can try. Yeah.